Let's go deep on one hard problem: teaching a humanoid to walk. Standing on two legs is unstable. It is like balancing a tall broom on your hand. The robot is always about to fall, and it must constantly push back to stay upright. For decades, engineers hand wrote the equations to control this. It works, but it is fragile, and it breaks on a new floor, a push, or a slope. So instead, we let the robot learn to walk by itself, using reinforcement learning. That is the only thing we explore here. Reinforcement learning is learning by trial and error. There is a policy, a neural network that is the robot's reflexes. Every fraction of a second, it reads an observation, the joint angles, the joint speeds, and the tilt from the inertial sensor. From that, it outputs an action, a target angle for every motor. The world then responds, and the robot gets a reward, a single number that says how good that moment was. The policy's only goal is to choose actions that pile up as much future reward as possible. Walk well, reward goes up. Fall over, reward crashes. But learning by falling is a problem. A real robot cannot fall a million times. It would destroy itself in an afternoon. So we train entirely in simulation, and here is the trick that changed everything: massively parallel simulation. On a single graphics card, we spin up thousands of copies of the robot at once, all walking, stumbling, and falling in parallel. Years of walking experience are compressed into minutes. One recent recipe trains a humanoid to walk in just 15 minutes on a single desktop GPU. Cheap, fast, and the robot never gets hurt. So what reward do we give? This is the heart of it. The reward is how we tell the robot what walking even means. A good recipe keeps it minimal. Reward the robot for matching the commanded velocity, go this fast in this direction. Reward it for staying upright, and gently penalize wasted energy and jerky motion so the gait comes out smooth and natural. Get this wrong, and the robot finds bizarre tricks that score high but look nothing like walking. The reward is the specification. Designing it well is most of the art. Now, the hardest part is the sim to real gap. The simulator is never the real world. Friction is a little off. The motors respond with a tiny delay. The robot's true weight is not exactly what we modeled. A policy that walks flawlessly in simulation will often faceplant the instant it touches the real floor. The physics it trained on simply does not match. Closing this gap is the central challenge of the entire field, and for years it was the reason learned controllers stayed trapped inside the simulator. The fix is beautiful and almost paradoxical: domain randomization. If we do not know the real friction, the real delay, the real mass, then do not pick one. Randomize all of them. Every episode, every one of those thousands of robots trains in a slightly different world. Different friction, different terrain, random pushes, random motor lag. The policy can no longer memorize one perfect physics. It is forced to find a strategy that survives across every world it has ever seen. And then the real world is just one more random world it can handle. That is how the robot walks on the very first try, with no tuning. We call it zero-shot transfer. One more piece makes it robust. Instead of reacting to only this instant, the policy reads a short history of past observations and actions. From that history, a transformer can quietly infer what world it is in: heavy load, slippery ground, a strong push, and adapt on the fly, without ever changing its weights. Put it together: learn by trial and error, train thousands of robots in parallel in minutes, shape a minimal reward, and randomize the physics so it survives reality. The result is a humanoid that walks outdoors, over grass and slopes, shrugging off shoves, having never once walked in the real world before deployment.